This is the last part of lecture 24, and I'm not gonna, teach you any new math here. What I want to do instead is I want to explain the physical meaning behind the different types of solutions we found to different differential equations. So, for example, when we looked at single second order system, the solutions were governed by the roots of the auxiliary equation. And when we looked at system of first order ODE, the solutions were governed by the eigenvalues of the matrix A in question. And these could be like real numbers that are different, or complex numbers, or real numbers that are the same. And what I want to do here is, in this brief section, is talk about what do those different cases mean. Because after all, calculus was invented by Newton to study physics problems. And it turns out that all these different cases actually have a very nice physical meaning. I'm going to focus only on the single second order equation. And I'm going to go back to my mass spring example where I had a block of mass K that's attached to a spring, of mass M attached to a spring of spring constant K. It's sitting on maybe a surface which has some friction. The constant in the frictional force is B. And the equation of motion for this was, so if I let the displacement be y of t, so this is some rest position 0, and the equation of motion for this block was my double prime plus by prime plus ky equals 0. And so, we saw how to solve this system, even given even the initial value problem, which is just an initial specification of position and velocity. And the types of solutions that we got depended on the roots of this auxiliary equation. So I want to just explain what the different cases mean. So first, let me just talk about a special case. The special case is B equals 0, which means no friction. So if there's no friction, then what do you expect to happen if you pull this block away from equilibrium and let it go? We expect it to just bounce back and forth forever. There's nothing, there's nothing slowing this down, and the energy is not being dissipated because there's no friction. And so you expect this to just oscillate back and forth. And now we're going to see how that comes out in this equation. So in this case, the differential equation is my double prime plus ky equals 0. And so the auxiliary polynomial is mr squared plus, my double prime, mr squared plus k equals 0. And so the roots are r equals plus or minus square root minus k over m, which are both imaginary, right? Because both, so all these quantities are positive, right? So mass is positive, spring constant is positive, and the friction constant is also positive. And so these are both imaginary roots. In fact, they're pure imaginary roots, equal to plus or minus square root k over m times I. And so in this case, the solutions, or the general solution, is that y of t is c1 times cosine, let's call this quantity omega of t, plus c2 sine omega of t, where omega is, I just don't want to keep writing square root k over m, so omega is this number square root k over m. Okay. So, okay, does this correspond to our notion of it's just going to oscillate forever? Well, if it was just a cosine or a sine, then that sure looks like it's just oscillation. But what does a linear combination of a cosine and a sine mean? What does it look like? So let's try to figure that out right now. So what does C1 cosine t C2 sine look like? And so here, there's sort of just a general easy trick I can do. I can just, so these are C1 and C2 are some arbitrary real numbers. So what I can do is I can make a little triangle with sides C1 and C2, side length C1 and C2. And then I can complete this triangle. This is a right triangle. And it's going to have some angle phi and some hypotenuse a. So a is going to be equal to square root C1 squared plus squared. And now I have this nice fact that C1 is equal to A sine phi and C2 is equal to A cosine phi, right? In this triangle. And so now I can plug these back into my original expression, and with these substitutions, I get that y of t is actually A sine phi cosine omega t plus A cosine phi sine omega t. And now you might, remember your high school trigonometry, and this is the formula for sine A plus sine B, right? So this is A sine phi plus omega. And so the answer is, well, a linear combination of a cosine and a sine actually just looks like a shifted sine wave, right? So sine omega t is going to be 0 at 0, and it's just going to be the sine function. But if I add this angle phi, what this is saying is I just shift everything by some phi. So at 0, this is going to give me sine phi. So it's just going to look like this, where this distance is phi. And A is going to scale the whole thing by A. And so actually this general solution is just a shifted scaled sine wave. And so this agrees with our intuition that if there's no friction, if you pull the mass a little bit, so that corresponds to you started at some point that's not 0, and then you let it go. Well, it's gonna oscillate, forever, like a sine wave. Okay, so now let's look at the general case. So the general case, uh, the auxiliary equation is mr squared plus br plus k, and this has roots b minus b plus or minus square root b squared minus 4mk over 2. And what these roots are, whether they're real or complex and so on, depends on this discriminant. So you have three cases. So in the first case, you have b squared minus 4mk is greater than 0. In this case, you have both roots real and distinct. So by the way, you can say something a little bit more about these roots. So for general quadratic equation, there could be any two real numbers. Remember, we know that m, b, and k are non-negative, right? I should have said non-negative earlier rather than positive. For example, b could be 0, but if these are non-negative, then b squared minus 4mk is less than b, right? So the roots are going to be minus b plus square root is b squared minus 4mk over 2, which is going to be negative, right? Because if I took negative b and I added something less than b to it, and the second root is also going to be negative. And so you're actually going to get two negative real roots in the special case where the ODE comes from a spring mass system. And so what that means is that the general solution is y of t equals c1 e to the r1t plus c2 e to the r2t, where both r1 and r2 are negative. And so if you plot this, depending on whether C1 and C2 are negative or positive, we're going to get one of three different possibilities. So if both C1 and C2 are positive, you're going to get something that looks like this, a decaying exponential. If C1 and C2 are negative, you're going to get the same thing, but like this. And if C1 is positive and C2 is negative, you might get something that looks like this. But the point I want to make is, in all three of these cases, there's no oscillation. Okay, so these graphs look very different from the sign that I drew on the previous slide, and so the high level summary is that if you have distinct real roots, you don't have oscillation, and such a system is called over damp. And what that basically means is that the friction is large enough that it counteracts the other forces in question. I mean, namely the spring force. And you can see that in this term here, right? B squared minus 4mk is big if B is big in some vague sense compared to M and K. Okay. So that's the interpretation of real roots. And the second case is when B squared minus 4mk is negative. And in this case, you're going to get the roots are going to be complex conjugate pairs. So alpha plus I beta, R2 is alpha minus I beta. And you can get what these alpha and beta are from the quadratic formula. I'm not going to draw it. But what does the general solution look like? Or what does the type, if you were to graph the solution, what would it look like? You'd get, well, that y of t is e to the alpha t times cosine beta t. So C1 cosine beta t plus C2 sine beta t. And one thing you can see from the quadratic formula is that this alpha is going to be negative, right? Because remember, alpha is the real part of the root, which is minus b, and b is positive, so alpha is negative. And so what does this type of function look like? Well, by what we did on the previous slide, it's just e to the alpha t times some sine, a sine phi plus beta t. Because, a linear combination of sine and cosine is just an offset of a scaling of a sine. And so if you plot this, it's actually a combination of the two behaviors that we saw earlier. So this, remember, alpha is negative. So it's like some sine function, but which is decaying exponentially. This is a horrible picture. Okay. But I mean, you can see better versions of all these pictures in section 4.9. But what's going on here is, the friction is causing this vibration to eventually die out. So it's not going to oscillate with the same magnitude forever. It's going to eventually go to zero. But it's not strong enough to prevent it from oscillating entirely, and this is called underdamped vibration. And here, you can look here, this happens when B squared minus MK is negative. This happens when there's low friction. I mean, I'm not making physically rigorous statements here, but that's the intuition. And then the third case is when you have a double root, so B squared minus 4mk equals 0. And in this case, you have R1 equals R2. So in this case, the quadratic equation has a single real root, and this root is going to be negative. It's going to be equal to minus b over 2, actually. So might as well write that. And in this case, the general solution is, we have to do this sort of trick where we got an exponential and t times an exponential. And here, I mean, the graphs look just like the first case. In other words, there's no oscillation. And this is called critically damped, because what that means is, if you increase the friction at all, it would become underdamped. And if you decrease the friction at all, it would become, it would become overdamped. And if you decrease the friction, it would become underdamped, which, in other words, it would oscillate. Okay. So anyway, I mean, the point of this was that, these numbers that you get from these equations have a very clear physical meaning. Complex numbers mean oscillation. Real numbers mean exponential decay.